Hello, everyone. Welcome to Lecture 10 on Introductory Statistics. In last lecture, we talked about some event operations like complements, the unions, intersections, and differences. And well, today in this lecture, we're going to talk about some probability rules about them. Okay, so the first probability rule we're going to talk about is the complement rule. So what is the complement rule? So let E be any event associated with a random experiment, then the probability of the complement of this event equals what? 1 minus the probability of this event. Okay, so here E complement is the complement of E, and so on. So this complement rule can be equivalently expressed as what? As probability of A, this event equals 1 minus the probability of the complement of this event, or the summation of the probability of this event plus the probability of the complement of this event equals 1. Okay, so this complement rule is very can be seen in the Venn diagram. So this is, say this is my E, then everything else outside that, that's going to be E complement, right? So this is going to be E complement. So you can see that the probability of E union E complement is going to be what? Everything, right? So inside, it is in E or not in E, right? So it is going to be the probability of the sample space now, which equals what? 1, all right? And since their E and E complement are disjoint or mutually exclusive, so we also have what? The probability of E union E complement equals what? Probability of E plus probability of E complement. So therefore, we have the summation plus probability of E complement equals 1. Okay, now if we minus probability of E on both sides, we are going to get this one, right? You minus the probability E on both sides, and you will get this equation. If you minus what? Subtract the probability of E complement, you will get this one, and so on, right? So this is the complement rule. Now let's just give you an example. If you flip a coin, right, you got a head or not a head. The probability of getting head and the probability of getting not getting head, so is going to be the summation is going to be exactly 1, right? So and is a female or male, right? The probability of a female equals 1 minus the probability of a male. And the probability of winning a lottery equals what? 1 minus the probability of not winning a lottery, right? So that is the complement rule. Okay. Consider this example, right? So drawing a card at random from a standard deck of playing cards, the sample space is going to be the set of all the 52 cards. A is the event that a face card is drawn. B is the event that a red card is drawn. Okay, so now what is the probability of A complement? Okay, so as we know, probability of A equals what? There are 12 face cards among 52 cards in the deck, right? So therefore, what? Using the complement rule, probability of not a face card, right? A complement is that the card drawn is not a face card, right? That's A complement. So it equals what? 1 minus the probability of A equals 1 minus 12 over 52, which is 40 over 52. Okay, so that is the probability of A complement, right? So similarly, we can see that the probability of B equals what? red card. So as we know, diamonds and hearts, right? Diamonds and hearts. So that's 26 out of 52. So then we have what? The probability of B complement equals 1 minus the probability of B. So equals what? 1 minus 26 over 52, which is 26 over 52, which is what? 1/2. So the probability of not a red card, right? So complement is not a red card. So as we know, that's going to be some black card, right? So the color is black. So therefore, the probability of getting a black card is 1/2. So we found this probability using the complement rule, okay? So that is the complement rule, is to find the probability of the complement. Okay, very good. Now, the second rule we are going to introduce is the addition rule. Okay, so what is the addition rule? Now, that A and B be any two events, whether they are mutually exclusive or not, right, associated with a random experiment, then we're going to have the probability of the union equals what? The probability of A plus probability of B minus the probability of their intersection. Okay, so this is the addition rule. Okay, so we can prove this one using Venn diagram. All right, so as we know, the union of A and B is everything either in A or B or both, right? So this one can be rewritten as the summation. Okay, so say this is our A and this is B. A and B. Now you can write this one as part A, okay, plus what? Plus the part that is in B but not in A, right? So this is A and this is B plus this part. Now, then this together will give us the probability of A union B, right? So in other words, we will have probability of A union B equals probability of A plus probability of A complement, right? Not in A, but in B. Okay. Now, let's consider this part, this one. All right. So this one is in B, not in A. So in B, not in A, it seems like just to exclude. Okay. So it is simply to exclude the dotted area here from B, right? Let's just exclude the dotted area. What is the dotted area? The dotted area is the intersection, right? So it is simply what? Probability of B minus the probability of the intersection. Okay, so that's what? Exclude the intersection from B. Okay, so that is what we have. Then this one, of course, equals what? Probability of A plus probability of B minus the probability of their intersection. Okay, so that's how we got the addition rule. Okay, that's how we got the addition rule. So what is the addition rule is used to find the probability of the union. Okay, so it is probability of A plus probability of B and minus, all right, minus the probability of the intersection. Okay, so be careful on that. And there is a special case here when A and B are mutually exclusive. What do we mean by mutually exclusive? That is what? A intersect B is empty, right? It's an empty set, it's a null event. In this case, the probability of the intersection is simply 0. So we're going to have this equation. But this equation holds only when what? They are mutually exclusive. Now, the addition rule can be equivalently expressed as follows. All right, so you have probability of the union equals the summation minus the probability of the intersection. So if you plus the intersection on both sides, you will get this equation. All right, And then if you minus probability of the union on both sides, you will get this one. All right, so these are equivalent forms of the addition rule. Now let's consider this this example again. Now let's see what is the probability of A union B. Okay, so what is the probability of A union B? So as we know, by addition rule, it should equals what? The probability of A plus probability of B, right? Be careful, minus the probability of their intersection. Now, this one equals what? This one equals the probability of A. As we know, that's a face card. So in total, there are 12 face cards among 52. Plus B is a red card. That's 26 out of 52. But in A and B, the intersection, as we know, it must be what? Face card and also red. So there are 3 face card in diamond and 3 face card in heart, right? So therefore, there are in total 6 face card and red. All right, so therefore, this probability of intersection is 6/52. And you can see that this is 32/52. Okay, that's probability of the union. All right, so you want to use what? Probability of A plus probability of B, but remember, minus the probability of the intersection. Now, if we let C be the event that a number card is drawn, right? So then probability of A intersect C. So as we see that A and C, one is the face card, the other is the number card, right? So they are what? They are mutually exclusive, right? So if it is a number card, it cannot be face card. If it is a face card, it can never be a number card. So A and C are what? Mutually exclusive. So by addition rule, this one is simply equals what? A plus probability of C, right? Equals, this is 12/52 plus what? There are 9 in each suit, so 36/52. 48/52, so that's 12/13. Okay, that's the probability of the union. Now this equation holds since what? Since A intersect C is null event. In other words, A and C are mutually exclusive. So therefore, we have this one equals this. Okay, so that's the addition rule. All right, what is addition rule? Addition rule is used to find the probability of the union of 2 events. All right, the union of 2 events. Now the next rule is about the difference rule. Now let A, B be 2 events associated with a random experiment. Then we have what? This probability in A, not in B. Okay, so it is the Venn diagram here. In A, not in B. So that's what? Here's A, here's B. So that is the part only in A, right? As you can see, it is to exclude the intersection part from A. So therefore, we have probability of A intersect B complement equals what? Probability of A minus the intersection, probability of the intersection. So exclude the intersection from A. Okay, so that is in A, not in B. Similarly, we have what? The second one, right? So if it is A and B, this is in B, not in A. So it is exclude this intersection from B, right? In B, not in A. So it is probability B minus probability of their intersection. Okay, so therefore we have all these equations, right? Probability of this, the first difference rule in A, not in B, is probability A minus the probability of the intersection. Well, in B, not in A, is the probability of B minus probability of the intersection. Now, these will be A intersect B, A intersect B. Complement is probability of A. So if you multiply if you add the probability of intersection on both sides, so you will get A intersect B complement plus probability of A intersect B equals what? Probability of A. So apparently, the shaded area and the dotted area, add them together, you got A, right? So, and similarly here, you have what? Probability of A complement intersect B plus probability of A intersect B, and you got what? Probability of B, right? So the dotted area plus the shaded area is the area B. Now this is the difference rule. Okay, so this is a difference rule, is to find the intersection of one event and the complement of another. So A intersect B complement or A complement intersect B. Okay. Now consider this example. All right, so we want to find here is A intersect B complement. Okay, so as we can see, A intersect B complement, that is to say what? It is a face card, but what? But not red. Face card, but not red. By definition, we know that is probability of A's minus probability of their intersection, the complement rule, right? This is the complement rule in A, not in B. So exclude the intersection from A. So therefore, this one equals A is 12 over 52. Intersection is 6 over 52. So therefore, this is 6 over 52. Okay. Now, similarly, probability of A complement intersected B equals probability of B minus probability of A intersected B. So this is in B, but not in A, right? It's in B, not in A. So that is what? It is a red card, but not a face card, right? It's a red card, but not a face card. So then this is 26 out of 52 minus 6 over 52. So which is 20 over 52. That's the difference rule. Okay, all right. So let's consider this is the three probability rules. One is a complement rule, the addition rule for the union, the difference rule for the differences, okay, of two events. Now consider this example. All right, drawing a card at random from the center deck of playing cards. Sample space is this one, and A is even a face card is drawn, B is even that a red card is drawn. We want to find the probability of these ones. So we already found these, right? And this one, and this, right? So we already found all these three, threes. Now the only question left is D, right? So how to find part B? For instance, how to find the probability of A union B complement? How do you think? How can we find this probability? Now, in order to find this probability, we need to use what? Firstly, what kind of probability rule should we use? Now, we see that this is a union, all right? This is the union of two events. One is A, the other is B complement. So we are going to use the addition rule because it is a union, right? So the union, remember the probability, the addition rule is what? A one event, another event is the probability of the first event plus the probability of the second event minus the probability of their intersection. Okay, so if we replace B by B complement, all right, replace B by B complement, so we are going to get the probability of this union, right? So it's going to be what? Probability of the first event, probability A, plus probability of the second event, that's B complement. All right, and minus what? the probability of the intersection of these two events. Now, the first event is A, the second event is B complement. Okay, so this is what we have. Now, probability A, that's 12 over 52. Probability of B complement, as we have found, to use what? Not red, so it's 26 over 52. We already found this, all right? So, and then this one is also known in part C, right? So we found this one in C is 6 over 52. So minus 6 over 52. So we have what? This is 32 over 52. Okay, so this is the first one. And then let's see the second one. A complement union B, right? So similarly, this is again a union. So we're going to use what? Use the addition rule. Okay, so that's going to be probability of A complement plus this is the first event plus probability of the second event minus the probability of the intersection. So it's the first one intersect the second one. So similarly, we know that this one equals what? 40 out of 52 plus, okay, now this one is B, here is 26 out of 52 minus, now this one we found in this part is 20 over 52. So minus 20 over 52, so you got this is 46 over 52. Okay, so that is the probability of this union. Okay, so this is another example, right? So now, how about let's solve another one. So what is going to be, for instance, I'm going to ask you this one. So what about the probability of the complement of the union? What about this one? The complement of this union A and B. Okay, so we're going to use what? This is the complement first, right? So you're using the complement rule. So it's 1 minus the probability of the union. So as we know, the union is already found when we talked about addition rule. So this union is already found here, 32 over 52. Okay, so we already found this union. Therefore, we can just plug in here. It's 1 minus 32 over 52. So that's 20 over 52. Okay, so that's the probability of this one, right? So we can get this. All right, so this uses the what? The complement rule, addition rule, difference rule, and addition rule, right? So we can use all this. Now, how about consider another example here? A and B are two events with A here B, and this one equals this one. So A, now what is the probability of A complement? Now, by complement rule, it is 1 minus probability of A equals 1 minus 0.5 equals 0.5. And similarly, using the complement rule, probability of B complement is 1 minus probability of B equals what? 1 minus 0.6 equals 0.4. Okay, now part of B, the union A union B using addition rule because it's a union, right? So it's the probability of the first event plus the probability of the second event minus the probability of their intersection, A and B. So we have all these values. This is 0.5 plus 0.6 minus 0.3. So we found this is 0.8. Okay. Now for C here is the probability of A intersect B complement. So using the difference rule, it's in A, not in B. So exclude the intersection from A. Okay, so excluding the intersection from A, so that's what? 0.5 minus 0.3 equals 0.2. And probability of A complement intersect B is to exclude the intersection from B. So probability B minus the probability of their intersection, so equals 0.6 minus 0.3, which is 0.3. And finally, D, now we know that this is A union B complement. That is using addition rule, probability of the first plus the probability of the second minus the probability of their intersection, okay, A and B complement. So then we have probability of A is 0.5. Probability of B complement, we already found this is 0.4. So 0.4 minus this A B complement, here is 0.2. So minus 0.2, that's 0.7. Okay. Now similarly, we can find A complement union B. Okay. So this is the probability of A complement plus probability of B minus probability of A intersect, A complement intersect B. So this is what? A complement, we already found that's 0.5 plus the probability of B is 0.6 minus this one in B, not in A, we found it's 0.3. So minus 0.3, so it's 0.8. We got these values. All right, so this is basically a similar example using what? The complement rule, the addition rule, the difference rule. Okay, so you need to know how to use all these probability rules. Now let's just continue with another example here. We roll a fair die. A is 1, 3, B is 2, 4, 6. Then we want to find these probabilities. Okay, so for instance, what is the probability of A complement? So since the rule fair die, the probability of 1 minus probability A, so there are 2 outcomes in this event A. So therefore is 1 minus what? 2 over 6. So it's 4 over 6 as 2/3. Okay, similarly, probability of B complement is 1 minus the probability of B. So is 1 minus what? For B, there are 3 outcomes, so it's 3 out of 6. So it's 3 out of 6, which is 1/2. And for B, the probability of A union B, now using addition rule, A plus probability of B minus probability of their intersection. This is going to be A here is probability A is 2 over 6, B is 3 over 6. The intersection. So what is the A intersected B? So A intersected B, as we know, it is 3. 1, 3, 2, 4, 6 is empty, right? It's a null event. So they have nothing in common, right? They have nothing in common. So therefore is what? Minus the probability of the null event. So it's simply what? 5 over 6, right? 5 over 6. So because what? This one is 0. C here is the probability of A intersect B complement. Again, using the difference rule is A minus probability of A intersect B. Now, again, this is probability A is 2 over 6 minus what? Probability of the intersection, which is the null event. So which is 2 over 6, which is 1 over 3. Similarly, probability of A complement intersect B equals exclude the intersection from B equals what? 3 over 6 minus the probability of the null event. So it's 3 over 6, it is 1/2, right? And finally, D, probability of A union B complement equals probability of A plus probability of B complement minus probability of A intersect B complement, right? So using addition rule, probability A is 2 over 6 plus the B complement is 3 over 6 here, okay? So minus this one is 1/3, okay? So 2 over 6. Now this one is 3 over 6 is 1/2, okay? Now finally this part, okay, probability of A complement union B, okay? A complement union B is going to be what? Probability of A complement, sorry, it's simply A complement plus probability of B minus probability of A complement intersect B, so which equals A complement is here is 4/6 minus this one is 1/2, it's 3/6, so it's 1/6, right? So we found all these values using these three rules: the complement rule, the addition rule, and the difference rule. Okay. All right, next we are going to move on to section 3 on conditional probability and independence. So firstly, what is conditional probability, right? So conditional probability is the probability of one event given that another event has occurred. Now, in many cases, these two events, the occurrence of one event influences the probability of the occurrence of another. Okay, so let me just give you an example. Now, say that you're driving 50 miles per hour on a local, in a local street. So it's considered to be very, very fast, right? Much faster than the speed limit. Let's say that. Okay, you're driving 20 miles per hour over the speed limit. Okay, then what? Your chance this event, your speeding, this event will influence the probability of you getting pulled over. You get pulled over is another event, right? So you're speeding, the occurrence of this event, the first event that you're speeding, influences the probability of the occurrence for you to be what? Got pulled over. So that is the conditional probability. So informally, we will say the conditional probability of this event given B. So there are two events here. One event is the event of interest. So here A is the event of interest. So we are trying to find the probability of A. Okay. Now, however, this probability is under a condition, right? B. So there's another event. B is the event that serves as the condition. Serves as the condition. Okay, so there are two events, right? So one event is the event of interest. The other event is the event that serves as a condition. So be careful. When we are talking about the conditional probabilities, there are two events. Now, one is the event of interest. The other is the event that serves as the condition. Now, the notation is given here. Okay, so be careful here again. Now, there is a bar separating what? Event A and B. So in front, the event in front of this bar is the event of interest. And the event after this bar, that's the event that serves as a condition. Okay, so we read the conditional probability of A given B. Okay, so this one is the probability of event A given that event B has already occurred. Okay, so that's the conditional probability. Now, this conditional probability can be found by what? This formula is dividing the probability of the intersection. So on the numerator, that's the probability of the intersection by the probability of the B, right? By the probability of B. So this uses the conditional probability of A given B. Now be careful. A is the event of interest. B is the event that serves as a condition. All right. So now, since the probability B is here, right, is probability B, if the event that serves as a condition is in the denominator, so we require what? This probability must be greater than 0. Now, consider ruling of Faraday. A is 3, 4 here, so B is the event consisting of 2, 4, 6. Then the conditional probability of A So this is the event of interest given that B has occurred, right? So that is what? That is, by definition, the probability of intersection over the probability of the event that serves as a condition. That's what? Probability of B, right? So on the top, that is A intersect B, as we see that A intersect B equals just 4, right? Just a 4 here. So that's what we have here, and probability B. So probability of singleton here, B, it's 4 is 1/6, right? And this is 3/6. So that's 1/3, right? So that's 1/3. Now the conditional probability of B given A has occurred is going to be by definition, all right? There B is the event of interest. A is the event that serves as a condition. So therefore, what on the top is again the intersection. Now here is a B intersect A equals what? A intersect B. They all the same, right? They're the same. So we can just write on the top A intersect B, right? So it's literally the same. And over the probability of the event that serves as a condition. So that is what now for this one, A is the event that serves as a condition. So therefore, here is the probability of A. And then here again, this is 1/6. For probability of A is 3 and 4. So therefore, the probability is 2/6. Therefore, we have this one, the conditional probability of B given A is 1/2. So we found these ones by definition, right? By definition. So be careful. This is on the top, a fraction. On the top, that's the probability of the intersection of these two events, A and B, or whatever, right? So one is the event of interest, the other is the event that serves as the condition. Now, however, in the denominator, okay, so that's the probability of B, okay, which is the event that serves as the condition. So be careful on that. Let's consider example here. Now, given this probability A is 0.5, 0.4, and B is 0.5, this conditional probability is 0.6. Now we are to find this and this and this. Now let's see how we can find the part A, okay? So now this one seems like we have this conditional probability is 0.6. So let's consider this one by definition. So this is going to be what? The probability of their intersection, right? A intersect B over what? The probability of B. Okay, so A intersect B over the probability of B. Okay, so that's by definition. We know that this conditional probability of A given B equals the probability of the intersection over the probability of B, which is the event that serves as a condition. So this one equals what? This one equals 0.6. 0.6. Okay. Now, therefore, we will know if we multiply probability of B on both sides. So this implies probability of A intersect B equals what? 0.6 times probability of B. So which equals 0.6 times 0.5 is 0.3. So therefore, we know that this probability of the intersection is simply 0.3. Similarly for part B, okay, so it's a conditional probability of A given that B complement. All right, be careful. This one, A is the event of interest. Now, the event that serves as a condition is now B complement. So therefore, what? Probability of A given B complement became what? The probability of the intersection of these two events. One is A, the other is B complement. So A intersect B complement over the probability of what? Probability of the event that serves as a condition. For this one, the event that serves as a condition is B complement. So therefore, here is B complement. Now, how can we find these values? It's not a given, right? It's not given. These values are not given. So how can we, then we need to find out these values. So on the top, that's in A, but not in B, right? In A, not in B, that's what? The difference rule. Remember difference rule? So in A, not in B, that's to exclude the intersection part from A. Okay, so that is this probability, the difference rule. Now for the bottom one is the probability of the complement of B. So it is what? It is using the complement rule, it's 1 minus the probability of B. Now it seems like everything is clear, right? So probability of A is 0.4. Now probability of intersection, as we found in A, is 0.3. And then this 1 minus probability of B is 0.5. Okay, so we found this 1 over 5, which is 0.2. Okay, now let's consider C. All right, how about C? Can we find the probability, this conditional probability? So for this C, right? So the event of interest is the complement of A, and the event serves as a condition is B. Okay, so how to find this? A complement given B. All right, so this is, again, by definition, that's the intersection of these two events. One is A complement, the other is B. So A complement intersect B. Now, over the bottom is the probability of the event that serves as a condition. For this one, the event that serves as a condition is B. So it's just over probability of B. So again, on the top, this is in B, not in A. So using the difference rule, exclude the intersection from B, right? From B over probability of B. Okay. Now we know that probability of B is 0.5. This is 0.3, and this is 0.5. So we found this is 2 over 5, which is 0.4. Okay, so that's how we find these values. All right, we found those by definition. So we need, in order to use a definition, you need to be really careful. All right, there are two events involved in a conditional probability. So one is the event of interest. That's the event in front of the bar, right? Now, another event is the event that serves as a condition. That is the event behind the bar. Right behind the bar. Okay, so and then you go from there and use the definition of conditional probability. You can find those values. Of course, some of them you need to use some probability rules, like the difference rule, like the complement rule, and so on. Okay, that is this example. Now let's consider another example about a conditional probability. So the probability that a regularly scheduled flight departs on time is probability of D equals 0.83. And the probability that it arrives on time is probability of A equals 0.82. The probability that it departs and arrives on time is the probability of the intersection of D and A equals what? 0.78. Now we want to find the following conditional probabilities: that a randomly selected flight A arrives on time given that it departed on time. B, it departed on time given that it has arrived on time. C, it arrives on time given that it departed late. Okay, so now that's the solution, right? So solution here, part A. Okay, so we need to know this is the conditional probability, and there are two events, right? Two events. Now for A here, the event of interest is arrives on time. We want to find the probability that it arrives on time. Now under the condition what? Under the condition given that it departed on time, right? So therefore, the event of interest is arrives on time. and the event that serves as a condition is it departed on time. So probability of A given D. Now this one equals what? The intersection I intersect D over the probability of the event that serves as a condition that's the departed on time, right? So then this one equals what? On the top, A intersect D equals D intersect A. So they are basically the same event, okay? So they are both what? It departs and arrives on time. So that is what? That is 0.78. This one is, D is 0.83. So it's 78 over 83. Okay, so that is part A, right? So you need to be really careful which event is the event of interest and which event is the event that serves as a condition. And then write down the correct form, use the definition, find this value. Okay, this is part A. Now let's consider part B. Okay, now it departed on time given that it has arrived on time. So now for this one, the event of interest is departed on time, right? And the condition is given that it has arrived on time, so it is this one. So therefore we have what? The intersection, D intersect A over probability what? Okay, be careful. Now the condition is A, so it's over probability of A. So it equals what? 0.78 over 0.82. So it equals what? 78 over 82. Okay. Now similarly, let's consider C. So arrives on time, and given that it departed late. So we know that probability of A is the event of interest, and the condition is departed late. Departed late means what? Means it is departed complement of D. All right, so that's the condition now. Now, by definition, we know that on the top, that's going to be A intersect D complement over the probability of what? The event that serves as a condition is departed late, the probability of D complement. So on the top, that's the what? Difference rule, all right, probability of A minus probability of the intersection of A and D. So on the bottom is the complement rule, 1 minus probability of D. So we got what? Probability A is 0.82 minus probability of intersection is 0.78. So 1 minus 0.83. So that's what? 0.04 over 0.17 is 4 over 17. Right, 4 over 17. All right, so very good. That's the this conditional probability. All right, so you need to be really careful on which is the event of interest and which is the event that serves as a condition. Okay, so when you got those two events, then you can use the definition to find the conditional probabilities. Okay, all right. So now let's move on to a very important rule called the product rule. Okay, so this one is, okay, for instance, A given B, by definition, it is the probability of their intersection over the probability of B. Now, if I multiply B on both probability of B on both sides, okay, so here multiply probability B on both sides, you see that this is canceled out. So we got what? We got the probability of the intersection equals probability of B times probability of A given B. All right, so now you can see that this is probability of B, this is probability of A given B, right? So now one thing you have to be really careful is here B is the event that serves as a condition, then in the front, that should be what? The probability of B, which is the event that serves as a condition. Okay, so now you can also use what? Probability of A intersect B. If you're using A here in the front, then this should be what? B given A. This is also true. Okay. Now, the key is, all right, so in the front, this should be the probability of the event that serves as the condition. Okay, serves as a condition. Okay, so and then times the conditional probability, right? So then this will be the product rule and the product rule. Consider this example. Two cards are drawn successfully from the stand deck of cards at random without replacement. Now we want to find the following probabilities. A, both of them are hearts. B, first is a heart and second is a spade. Okay, now, firstly, I want to make sure that we understand what do we mean by without replacement, without replacement. Okay, so this is a selection method, right? If it is without replacement, being basically you draw one card, okay, and when you draw the second card, you do not replace the first card back to the deck. Okay, so which means you draw one and then draw another one, right? And then you draw another one. So that means without replacement. Now with replacement means what? You draw one and see the result, and you replace, right? Put it back, and then draw another one, right? So that's with replacement. Here we are talking about without replacement. Okay, so now let's see how can we solve part A first. Now both of them are hearts. Now let's firstly define some events. Right? Let what H1 be the event that the first draw is a heart. All right. So and what? Let H2 be the event that the second draw is a heart. Okay, so therefore what? The probability of both are heart. So this means what? The probability the first is heart and the probability for the second to be heart, right? So this is what? The first is a heart and the second is a heart. So both of them are hearts. Then we're going to use the product rule. Okay, so the product rule, now we want to use what? Following the order. All right, usually it's following the order of this one. So now firstly, you need to have the first one is a heart. Okay, now probability of H1. So then if this is a probability of H1, then for the conditional probability followed, as you can see, this should be what? H1 should be a condition serves in the conditional probability, right? So therefore, what is the conditional probability of? Okay, this is H1, and this is the interest is H2. Even if interest is H2, and the condition is H1. So basically, it means what? Probability that the first is a heart, and the second term is that given that the first is a heart, what is the probability that the second is a heart, right? So then this one equals what? This one probability of H1. The first is the heart. So what is the probability that the first is the heart? So it is 13 out of 52, right? 13 out of 52. Now multiply, given that the first is a heart, how many cards are left? So there are 51 cards are left, right? So because it's without replacement. Now if the first is a heart, then there are 51 cards left, among which, how many hearts are there? Oh, there should be what? 12 hearts in the remaining 51, right? So 12 hearts from the remaining 51 cards. So therefore, this conditional probability will be what? 12 over 51. Okay, so you can find that this is 1/4 is 3/51. Okay, 3/51. B. Okay, so first is the heart. Okay, now again you can just let what S2. All right, second is the spade. Be the event that the second is a spade. So therefore, what this probability is, the first is the heart, and the second is a spade, is going to be this probability. So similarly using the product rule, probability of H1 times the probability of S2 given H1. So this one is the same as the 13/52. Now, what about this conditional probability? What is this? Given that the first is the heart, what is the conditional probability that the second is a spade? So again, there are 51 cards remaining, among which there are what? 13 spades. So this conditional probability is what? 13 out of 51, or 13 out of 51. Be careful on that. So this will be what? This will be 13/204. Right, 13/204. Okay, so that is this second B. Okay, so be careful here. We use the what? The product rule, right? So by using the product rule, we can find these probabilities. Now, you have to be careful. If this is H1, then for the conditional probability here, H1 serves as a condition. Okay, so usually it's follow some sequential order, right? You draw the first and then the second. So that's why we are having this. Now consider another example here. The probability that a doctor in a local hospital correctly diagnoses a particular illness is 0.85, right? Given that the doctor makes an incorrect diagnosis, the conditional probability that a patient files a lawsuit is 0.9. So what is the probability that doctor makes an incorrect diagnosis and the patient sues? Okay, so let's consider this one here, right? Solution. Now let's define some events. All right, let what? A be the event. Now see that it is correctly diagnosed, or the doctor correctly diagnoses the disease, the illness, right? The illness. Okay, and what? Let B be the event. What? Be the event that the patient files a lawsuit, right? The patient sues. The patient sues. Okay. Now, therefore, what we are trying to ask, what is the probability that the doctor makes an incorrect diagnosis and the patient sues? So basically, what it should be well, here is a correctly diagnosed. So we're talking about the incorrect diagnosis. So that's going to be what? The complement of A, right? The complement of A intersect what? Intersect B. Okay, so intersect B and the patient sues. Now for this one, there is a logical reason. The doctor need to what? To make an incorrect diagnosis, then the patient sues, right? So we are going to firstly A complement, then times what? Probability of B given A complement. Okay, so this makes sense, right? So probability of it makes an incorrect diagnosis, and then the conditional probability of the patient's use given that it makes an incorrect diagnosis. So now, what is this first? This one is probably a complement, which means the probability that doctor makes an incorrect diagnosis. So we know that the correctly diagnosed is 0.85, so this probability is 1 minus 0.85, right? And then this conditional probability is what? As from the second sentence, given makes an incorrect diagnosis, conditional probability that lawsuit is 0.9. So this conditional probability is 0.9. So which is what? 0.15 times 0.9. So use the calculator. What we have? 0.135. Yes, right? 0.135. So that is the conditional probability we have here. Right? So you firstly define our events, and then we can use the product rule to find the probability of the intersection. Okay, so that is this example. Okay. All right. I'm going to stop here for this lecture, and we're going to continue in the next one. Thank you for your attention, and see you next time. Bye-bye.